Okay, hello everybody. I just want to make a brief video after having walked through the concept of z-scores in the last video to give you some examples of how to calculate z-scores for data you might encounter in the real world. Still not going to use language data yet, but we're going to talk about height and the weather again. Uh, yeah, so because we've seen those before and hopefully they'll be relatively familiar to common everyday experience. Uh, yeah, so without any further ado, this is normally an exercise that we walk through together in class, just on the board, kind of on the fly. And there is a kind of a point to it by the time we get to the end. But just so you know, we'll be focusing on height. And normally what we do is we calculate everybody's height in terms of the z-scores for that height. So I would normally have you do this like with pencil and paper in a class, but we don't have that luxury at the moment. So I'm just going to do it for my own height, which I happen to know. And so I'm going to do it using PowerPoint as well. So you don't have to scribble anything out at the moment, but hopefully follow along and make sure you understand what I'm doing. And it's not too complicated once you get the hang of it, because like I said, it's basically a linear transformation. So you just have to know the algebra and the right sort of numbers to put into the variables. But we're going to start by basing our z-scores on the height data that I posted to the course website. This is... Yeah, actually, I don't really need to copy this link, but I'm going to post it for you there. And it's in this datasets link on the course website right here. This is from, again, 2 years ago, and this shows you like all the datasets we wind up working through at the end. But this is the one I'm looking at here, the men's and women's height. We've seen that before. And I might as well just load it into R. We know how to do this now. We'll just call it height. And we'll say that it's this. And we can copy that like that and make sure we put that little header equals t in there, because the first line of this has this line saying observation for men and women. And now we know we can kind of divvy up height by the two sexes as well. And so for my z-score, we'll calculate it with respect to men. And so yeah, the PowerPoint shows you the kind of crucial variables or the crucial information you need to know to do this, which is the mean of the height for men and the standard deviation of the height for men. So I'll take this another step here, and actually I didn't really do that right. So if we go mean height men in R, it tells you exactly what you see on the slide, and we go standard deviation SD, we get the same information. That's exactly where I got it from, right? So it's not hard to do that if you just want to know those specific numbers. I've got a little note here on the slide too that these are in inches. So the average height for men is about 69.5 inches, which is 5'9.5" for whatever that's worth. But if you don't like thinking in terms of inches for whatever reason, then you can just multiply that by 2.54, which is the conversion you use to go from inches to centimeters. You don't need to do anything more complicated than that. There's not like a slope and an intercept. It's just the slope, basically, as it were, and the intercept is 0. But that gives you an average height in metric of 176 centimeters for men, which is 1.76 meters. Okay, so I'm not going to say anything more about that. I will say just a little bit about how to calculate the z-score, though, right? Because that's why we're here. So our equation for z-scores looks like this. The z-score of whatever observation x you have, it equals x minus mu, the mean of the distribution, all that divided by sigma, which is the standard deviation of the distribution. Now remember, technically speaking, that I first presented this equation to you in terms of, idealized mathematically defined normal distribution, like the actual Gaussian distribution, using the equation that Gauss came up with a long time ago, right? So technically speaking, when we're looking at like the heights of men and women or whoever, we're not going to be using sort of these idealized variables like mu and sigma. We're going to be using x bar for the mean instead, and s for the standard deviation, because we just have a sample of some heights of some people, and we're not basing those parameters on like a mathematically defined function of some sort. We're getting those numbers out of like measured heights from specific people out in the world, presumably. I mean, I grabbed it from like a textbook, but that's of course where they got it from. So these are not representative of like all the heights of all the people in the world, or even like the idea that there might be some sort of height function that we all fall on that's defined mathematically. It's not really the case. We just have a distribution of heights, which is pretty close to normally distributed in the world. It happens to, just so happens to be the case. So anyways, just try to keep that technical distinction in mind. We're dealing with these sort of sample parameters, X bar and S. Those represent the numbers that I showed you on the previous slide. So substitute X bar for mu here and S for sigma, and just walk through the math. So my height, it turns out, is about 6'3", or I'm about 75 inches tall. So all I need to do there is to substitute this number for the X in that equation, and then substitute the other numbers that we calculated on the previous slide in the relevant slots. So the Z-score for me is 75 minus the average height for men. All that difference divided by the standard deviation of the height for men. So that gives me about 5.36. That's the difference on the top of the fraction here in the numerator. And you divide that by 2.86 whatever, and you get a Z-score of 1.87. Okay, so my height is about not quite 2 standard deviations above the mean height for men. So that's on the high side. You can actually use this p-norm function in R to convert that into sort of a proportion of the distribution. So a z-score of 1.87, whether it's about height or temperature or whatever else, we'll look at it for, like, say, F0 or formant frequencies, whatever, it converts to 96.9. So that means that in this particular case, I'm taller than about 96.9% of men. Which is a fair number of them, but it's not all. It's always going to be the case, right? But that's just where I fall on that particular spot on the distribution. Yeah, and what I want to do next, just for kicks, is to figure out what would the equivalent height for women be. So if you know that a woman has the Z-score height, if you know that she's taller than 96.9% of women, what is the actual height value? And to do this, all we need to do is sort of walk through the algebra to kind of work backwards from this equation to solve for X in terms of these other variables. So we know, let's say, what the Z-score is for a particular woman's height, and we need to find out from our data what the average woman's height and the mean women's height in the standard deviation of women's height is. And knowing those three variables, we can solve for this fourth one, which is what is the actual height of this particular woman who has a z-score height of 1.87. Yeah, so if we go back to the little data set, we can find that for women, the average or mean height is going to be 64.33 inches based on that data set. So it's a little bit different from what we saw in the previous lecture where we're talking about 64.5, but it's basically the same, right? And on the previous lecture, we said the standard deviation was 2.5. In this particular data set, it winds up being like 2.7 inches. And just also for reference's sake, if you're used to thinking about this in terms of like feet and inches, 64.33 inches is 5'4". Yeah, so that's an average height for a woman, and this is standard deviation, which is probably not something you've thought about before, but either way, kind of works out to pretty close to the values we had before. All we need to know now is the algebra, or sort of the reverse engineering of going from a z-score to figuring out what the underlying x value is for this particular example. So we know that the z-score that we're dealing with here is 1.87, and we're going to do some algebra to this particular equation. And again, this is something I normally write up on the board. But let's say we want to solve for x here. The first thing we do is multiply both sides of the equation by sigma to get the sigma out of this side, and then we wind up with sigma times z-score of x equals this difference, x minus mu. We can add mu to both sides of this equation here and get sigma times the z-score of x plus mu equals x. And then we're done with the algebra. We just need to kind of fill in the relevant values for the equation to figure out what x is. But remember, basically what this is saying is that x is going to equal the standard deviation times the z-score plus the mean of that distribution. Yeah, so if we just plug in the numbers, some of these numbers are maybe longer than we really need to know, but we get x being equal to 2.7 blah 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 times 1.87 plus the mean height for women, which is 64.33. That works out to being a height of 69.4 inches, which is about 5'9", which totally coincidentally is about the average height for a man. I think we saw the other slide, 69.4. Yeah, 69.64. So yeah, whatever. If you're a woman, you're 5'9". You're taller than about 96.9% of the rest of the world's women, more or less. Okay, so kind of working both ways there. Another part of this exercise that I normally work through in class, which is kind of the interesting part, is that I have everybody calculate their own z-scores for their own height. And then we kind of talk about them together. So I've done this in the past, and this also kind of like expands our view of what you can kind of expect in terms of z-scores. By referring it to something that, you know, is personal and familiar to you. But this is the z-score heights of every single student who's taken this class since 2013. And I start off with the men here because for whatever reason, fewer men have taken this class than women. And so with less space on this slide, I'm able to fit in all the men's heights. We'll do the women on the next slide. There's no other reason for the order there. So this gives you some examples here. So I actually included mine here. So we've seen that before. 75 inches converts into 1.87 in terms of z-scores. If a guy's height is going to be below the average, like 69.6, that's going to wind up giving you a negative z-score. So a height of 67 gives you a negative 0.92 z-score, so on and so forth. There's just a few more in here, but some are positive, some are negative. They're, you know, distributed on either side of the mean, as you might expect. This guy was almost right on the average there at the end. I don't want to dwell on that too much. You can do this exercise for yourself if you want to. And if you know your height in centimeters, then you can divide it by 2.54 to get it to inches, whatever. Convert your own height into z-scores. You should see something in the neighborhood of these values. We've had a few pretty tall women in this class over the years who have z-scores of over 2. No such examples for the men. And then, as usual, just a smattering of positives and negatives on either side of the mean of the distribution. Again, not going to dwell on this any further, but I do want to kind of, here's the data. And, you know, the data for the men is on this slide as well. What I want to ask, having gone through this exercise, and this is what I do normally ask in class, is, well, there are 28 observations in total in this sample. If they're normally distributed, how many z-scores would we expect to be positive? And you can think about that for a second. But remember, the normal distribution is symmetric, right? So there should be just as many positive z-scores as there are negative z-scores. And so if you have 28 and you're evenly dividing that in half for both the positives and negatives, you'd expect 14 of these z-scores to be positive. Well, how many z-scores do we actually have that are positive? It turns out we have 16. So that's pretty close, but remember, we're dealing with real data here, which kind of looks normally distributed, but is not based on some, you know, mathematical function. So it's not an actual representation of that Gaussian distribution. It's going to be pretty close, but not exact. And then the other thing I want to walk you through is that rule of thumb we have for normal distribution. So how many measurements should we expect to be within one standard deviation of the mean? I've taken a lot of drinks of water recently, so I'm not going to take another, but I will let you think about that. What's the answer to that question? And I'll show you that my famous clock now is running out of battery, so it's kind of dying there. I need to get a new one. Hopefully you're not running out of batteries, and hopefully you remembered that the rule of thumb there is that you should expect 68% of a normal distribution to fall within one standard deviation of the mean. So in this case, the way to get the answer here is to say multiply 68% by 28, which is the number of observations in the sample, and then you get a number of 19. So you'd expect 19 to be in that range. What do we actually observe in this data set? We get 22. Okay, so that's a little bit more. So we've got a little bit more on the high side. We've got a little bit more sort of in the middle there. What's the rule of thumb for within 2 standard deviations of the mean? Hopefully you can remember that's 95%. And so to get that expected number, we multiply 28 by 95%, which should give us 27. We're close to that. Remember I showed you there were a few women who had more height greater than 20 or greater than 2 standard deviations from the mean. And so our observation there is 26. Hopefully that's right. I think I actually saw 3 women with more than 2. No, yeah, okay. So we might want to knock one of those down. I'm not going to double check my arithmetic here, but I might have replicated more than one of these. Anyways, it's in the neighborhood. It's pretty close to what the math would predict, but it's not exact as before. So, right. And the funny thing is, and this works better when you're in a room of just students who just happen to be there because they wanted to take the class. Like nothing was bringing you there or would bring you there to a class other than the fact that you wanted to learn the material, right? But it turns out when you do that, you just grab some people from the world who have some interest and you look at their heights. Their heights are going to be more or less normally distributed, as if there's, some sort of magical puppeteer like dangling them on that bell curve line, even though they have really nothing else to do with each other. Isn't that weird? Yeah, it's just the way that height works out because it has that sort of underlying distribution. You grab any sort of people, any group of people, and they should follow that pattern more or less, even though it's not exact. There's always a little bit of random variation in it. Yeah, but that's a cool thing about stats is that you wind up seeing it wherever. Yeah, so the interim moral of the story, which I've said before, aside from the thing I just said a second ago, is that the height observations are in the neighborhood of being normal, but they're not exactly what the math would predict. This is what we'd expect from any sampling of data, however, if the underlying or population distribution is itself normal. So in the next week or so, we're going to learn how to determine whether the observed data that you have in some sample of data deviates meaningfully from an idealized normal distribution. So, like I said, when we first talked about distribution shapes, is that a lot of people think normal distributions are sort of like the default distributions in the world. And it turns out that's not really the case, but you might go into it thinking, my F0 measures, we can expect them to be normal or something like that. And then you look at them and you're like, it doesn't really look normal, but then like, how can I tell exactly? So to a certain extent, you can eyeball it, and that's what we're going to start out doing. But then when we learn how to do hypothesis testing, you can actually apply a test to the data and say, well, this is close enough to being normal for me to just treat it like it's normal, and I can do sort of like calculate z-scores on it. And then there's the criterion you use to say, well, no, that's far away enough from being normal to say I can't really do the sort of normal z-score stuff or whatever else I would do with a normal distribution. So yeah, there's another algorithm or rule of thumb you can use there. But again, another moral here is that things that might be normally distributed won't be exactly normally distributed, and then also don't assume that things will be normally distributed. Even if they're pretty close, there's a way you can kind of tell. Okay, so I'm going to give you one more translation here. We kind of went back and forth between male and female heights there. One thing you can do, which is even a little more dramatic, is you can compare the values of distributions of otherwise seemingly incomparable variables. And this is where the weather is going to come into play. Sorry for keep going back to this topic, but we're going to do another z-score exercise involving the high temperatures throughout the history of the city of Calgary. News, by the way, it's cooled down here considerably. I think in terms of Celsius temperatures, it's about 15 degrees. It's like 60 in terms of Fahrenheit. It's a lot easier to lecture in my office today. But be that as it may, a couple of days ago, it was still warm. So I want to calculate the z-score for the temperature. I have it yesterday on the slide, but it was 2 days ago now. And the high temperature in Calgary was 30.1 C, which is 86 degrees Fahrenheit if you're keeping score. So what's that? And to do that, I've actually worked out the math there, but again, I'll show you that you can get that weather data from here. And I think I will do this as well. I'll load it into R just so you can see how this works. And that has a header equals T. And it takes a while to load up because I actually, this is all the weather data that I was able to collect when I collected it the first time I taught this class in 2011. It turns out Environment Canada hasn't really updated this data since, so I'm glad I got it then. But it goes back to 1881, which is about the time Calgary was founded, right? And they're like, oh, first thing we got to do is set up a weather station and keep track of the weather here because we want to know why doesn't it get warmer in the summer. So anyways, way to kind of boil this down to just the Calgary part of it is to just subset it out and say, give me only the stuff where we have the city of Calgary, and make sure you get the syntax right. Not like that, but like that. Okay, sorry about that. Again, it's good to see other people's mistakes because then you know how to fix them. This just gives me the Calgary data. And if I want to sort of find out what's the average high temperature in Calgary, it turns out it's about 10.3 Celsius, which is about 50 degrees Fahrenheit. And if I look at the standard deviation, it's actually pretty broad. It's about 12.3 degrees Celsius, whatever that means. So if I take yesterday's or the 2nd of July's high and figure out its Z-score value, what I do is I take that particular value of 30.1 and then subtract 10.3 or the average high from it, and then I divide that difference by 12.3. If you do the math, you wind up getting a Z-score of 1.6. Normally I teach this class in January, and we do the same exercise for like whatever particular day in January it is. Because I'm doing this over the summer, I actually did the same exercise for the same right date, July 2nd. And I found out something kind of funny. So as you might expect, the average high on July 2nd in Calgary is much higher than the average high for Calgary over the entire year. It's 21.9, which is about 71 degrees Fahrenheit. But its standard deviation is much lower. It's 4.85. So you get a lot of variability in the high temperatures in Calgary. And when you actually work out the Z-score value for that particular high temperature we had 2 days ago, it winds up being 1.68 for just July 2nd, just that data alone, which surprisingly is higher than the Z-score value for Calgary overall. I was expecting it to be higher for Calgary overall because it's normally July is the warmest month basically in Calgary, and 30.1 is much higher than 10.3. That's a much higher temperature within that range, or it seems. But the standard deviation is so much bigger for Calgary overall throughout the entire year that the Z-score itself winds up being a little bit smaller when we plug this number into this equation for the overall highs throughout the year. So yeah, it was a good July 2nd, I guess, in terms of the weather. Nice and balmy, 30 degrees Celsius. So, right. And that converts to a nice high Z-score, basically. The kind of funny thing I want to do here at the very end of this is to show you how you can now translate between temperature and height using Z-score. So these are two sorts of variables which don't really have any meaningful relationship to each other than the fact that they're basically normally distributed. So when you do that, you can think of temperature in terms of its height, or height in terms of its temperature, I guess is the way I would say it. So what I'm going to do is, what I have students do in class is to express their height in terms of the corresponding Calgary high temperature for that score. And we'll do that, number one, by using this equation again that we worked out just a second ago in terms of like figuring out what the particular observation should be for a given Z-score of a variable. And then also we're going to do it for the overall throughout the year temperatures for Calgary. And I'll use my particular Z-score height because it's the only one I happen to know, since I don't know exactly who I'm talking to in this video right now. Anyways, if we do that, you just plug in the numbers. Again, it's the standard deviation times the Z-score plus the mean should give you the actual X value for that particular height or that particular Z-score. So if you have a height, if you have a male height of 1.87 Z-scores, you're 6'3". If you punch the numbers into this equation for temperature, you wind up with a high temperature of 33.37 degrees Celsius, which is something like 92 degrees Fahrenheit. So like my height converts into a high temperature of 33 degrees Celsius. Yeah. Right. So it's kind of funny to think, if we had a day, we actually, the day before, 2 days ago, it was around that high temperature in Calgary. So you could say, well, like that day was so hot, it was 6 feet tall, something like that. So whatever. You can do this for the particular day too. So if I do this for the July 2nd data, then I get a temperature of 31 degrees Celsius, which is a little bit less again, but that just kind of goes to show you this little odd finding I had that since the variation is so much less on July 2nd, you wind up with sort of a more condensed Z-score. Either way, though, you can go back and forth. I'll leave it up to you as an exercise to the reader. If you want to take some particular high temperature for Calgary, maybe the one today, it's like I said, it's 10 or 15 degrees Celsius, convert that into a height. It'll be closer to like sort of the average height for whatever group of people you're working with, men or women or whatever. But yeah, you can do that if you want to. And that turns out to be what we wind up doing basically when we try to sort of apply a Z-score transformation to whatever data we're playing around with. A good sample of sort of phonetics data you can normally apply Z-score transformations to are like VOT, voice onset time, depending on where you're getting it from. But you can think of, say, VOTs in terms of like temperatures or heights or whatever happens to be normally distributed in your life. We're going to say that again for homework exercises, but this is just a few examples so you know how Z-scores work. I'm going to walk you through some code next so we can also see where we get normal distributions from. But otherwise, that's all I've got to say for now. So I will see you next time. Stay warm and stay tall or whatever height you are too. Bye.